Welcome back to the course entitled Symmetry, Stereochemistry and Applications. In the last couple of lectures, we have discussed about topicity of ligands and phases. We have discussed about how to identify the diastereomers in alene systems and how to identify them as in terms of R and S isomers. So, in today's lecture, we will discuss about some of the problems that may be asked in the exams that we will face in this course. Let us understand the subject in depth by solving some of the problems. So, I am giving you the example of an alene where the alene may contain stereocenters as well. So, the question is, I am drawing one alene here which in turn has a chiral center here with groups as I am marking them HS or SH. The back side one is hydrogen and this one is methyl. Similarly, this group has one thiol here, back side is hydrogen and this one is methyl, and you have bromine and hydrogen on the other carbon. So, now if I ask you to identify whether this molecule is R or S, we need to first identify the chirality of those two chiral centers, because otherwise those two groups which are there on carbon 1 are identical. The chemical formula is identical. So, when you try to name this molecule or identify the chirality of this molecule, we first need to identify the chirality of those two carbons. So, now if we look at the top carbon, here what we have is hydrogen at the back, which is the fourth priority group. Highest priority group is above the plane and the other two groups are here. So, in terms of priority, this is 1. This group gets priority 2 because this is then connected to carbon, another carbon here, another carbon. So, this group has overall much larger molecular weight. So, this is 2, this is 3. So, here what we see is 1 to 2 to 3 is anti-clockwise and we are looking from the side opposite to the lowest prior group hydrogen. So, this must be S. In the same way, here this has priority 1, this back group has priority 2, this has a priority 3 and the hydrogen has priority 4. So, for this carbon, if we go from 1 to 2 to 3, we see that it is clockwise. So, it must be R. So, the absolute configuration of this center is R and that top center is S. So, now we need to know whether R or S gets priority when they are compared among themselves. See, according to CIP nomenclature rule, R gets priority over S. Now, let us assume the name of this group as A. So, the group with S configuration is AS and the group with R configuration is AR. So, if we draw the molecule now without drawing the large groups as it is, we write as AS and AR and draw the other two atoms on the carbon 3 as above and below the plane. So, now if we are looking at the molecule from this side, as you know, does not matter from which side we look at a molecule, the absolute configuration does not change. So, when we look at this from this side, we give priority 1, 2, 3, and when we were looking at it, this carbon 1 has the AS group pointing upwards, AR group also pointing upwards. On the back carbon, the bromine is pointing downwards on the right hand side, and the hydrogen on the left hand side once again pointing downward. Now, this is not the correct way of Fischer projection. So, what we should do is we should rotate the molecule in plane by 90 degree, maybe in the opposite direction, so that the hydrogen, which is the lowest priority group, comes at the bottom. So, we rotate it 90 degree in this direction. So, what we get is this one. So, now based on the priorities, we know that AR has higher priority over AS. So, this is 1, that is 2, this is 3, and hydrogen is 4. Okay, anyway, let us draw the Fischer projection, then we will write the designation. AR with priority 1, AS with priority 2, bromine with priority 3, and hydrogen with priority 4. So, here 1, 2, 2, 2, 3 is clockwise. So, the absolute configuration is R. So, the absolute configuration of this chiral axis is found to be R. Is it clear? So, if it is like that, then I would like you to try to understand or try to find out the stereochemical designation of a spiro compound which contains oxygen in the ring. So, now you see that this pivot atom at the point, from there we should start and number the chains, number the rings, keeping the center untouched. The numbering should be 1, 2, 3, 4, 5, 6, 7, 8 and 9. As per IUPAC nomenclature, we should simply write the name as 1,6 dioxa spiro 4.4 1, 2, 3, 4, 5, 6, 7, 8, 9. So, it is non-N. But you see that this compound is now chiral because of that spirocarbon, and this being a chiral axis, just like a biphenyl system. So, this chiral center has to be identified with the corresponding designation of R or S. So, now if we look at this molecule, suppose from this side, what we see is that on the top you have O and bottom you have carbon, but those are coming above and below and they are connected, and from this on the right we have oxygen and left we have carbon, which are also connected in turn. So, on the first carbon you have priority on this as 1, this one is 2, this is 3, that is 4. Now, this is not the Fisher projection method, because these two groups on the carbon 1 are above the plane. So, we should rotate it in plane by 90 degree to arrive at this configuration, this orientation, where O1, C2 are like that and O3 and C4 comes like this. So, if you draw the Fisher projection, it should look like this. Priorities are 1, 2, 3 and 4. So, now if we do it from 1 to 2 to 3, it is anti-clockwise. So, this configuration is S, right. Fourth group is in the vertical line. So, this should be S, and this S configuration is at point number 5. So, we should name this as 5S. So, this completes the IUPAC name of this particular compound. Hope this is clear to you. So, for you, I would like to give one problem related to this as a homework. Take this molecule and try to write the name of this molecule, the IUPAC name of this molecule, considering the stereochemistry of the chiral centers. Right. This is also another spiro compound, and you have two chiral centers here, and this point is the axially chiral center. So, you need to identify the chiralities of those three different chiral centers. Now, I would like to move to the next part of the problems, where we will try to identify the number of stereoisomers that are possible for different types of molecules. So, in this molecule what we see is a CC double bond, and we have two different substitutions here, and we have two substitutions which are in terms of atom they are same because they are chlorine, but you see that they may have a different stereochemistry at these 2 points. So, let us try to see what are the possible enantiomers of this compound. So, this is one of the isomers of this compound, where you have hydrogen and CO2H in this direction, and you have chlorine and chlorine up and chlorine down. So, if we see at this molecule, this chlorine gets priority 1, this carbon gets priority 2 because this is then connected to chlorine, and that carbon gets priority 3 because it gets connected to a second carbon. So, here we look at it 1 to 2 to 3 is anti-clockwise. So, it is S and hydrogen is at the back. In this particular case, this is 1, that is 2 and this is 3. So, it is 1 to 2 to 3 is clockwise, but then we are looking at it from the direction of this. So, this is S. So, both of them being S, this has only one isomer, because for this group what we have here is like a double bonded carbon with hydrogen and CO2H, and two groups are same. So, this has only one isomer. The only possibility is to have this as SS or RR. So, this is the SS form and that is the RR form. So, you have one isomer which is SS, the other isomer is RR, and there is no geometric isomer possible for this. But then when we have the opposite one, which is like this, both the chlorine atoms are above the plane. So, we write the priorities as 1, 2, 3. So, 1 to 2 to 3 anti-clockwise is S, and here it is 1 to 2 to 3 is clockwise. So, it is R. So, now we have one possibility of having both R group which is more prior here and more prior there on the same side, or we have another possibility of having the molecule like this, where these groups are interchanged, that is so here it is SR, where R and CO2H are on the same side. Here it is RS, where R and CO2H are in the opposite side. So, these two are a pair of diastereomers and these are two different isomers which are RR and SS. So, they are pairs of enantiomers. In the same way, I would like you to draw the possible stereoisomers of this compound. and find out which one of them are enantiomers, diastereomers, and whether there is any meso compound that is possible in this case. Now, we would like to move to the next part, which was discussed in the last couple of lectures, the topicity of different atoms and phases. So, I would like you to find out the topicity of the hydrogens that are marked here. One compound is this one, the other compound is this molecule. And then third compound that I want you to try to find out the topicity of the hydrogens is this one. So, how do we find it out? We first try to replace one by one, replace Ha by suppose Cl, and we get this molecule. And if we replace Hb by Cl, we get this molecule. So, if you look at these two molecules carefully, what we see that these two compounds are same. So, these compounds are to be called as homomers. Therefore, those two hydrogens are to be termed as homotopic. Let us try to see what happens if we replace this Ha and Hb separately by chlorine. We would get two different molecules. So, what we see here are these two are chiral compounds, but they are a pair of diastereomers because they are not related by any mirror image. So, these two hydrogens are diastereotopic. So, now if we try to do the same operation on these two hydrogens, we replace them one by chlorine. Let us see what happens. These two are non-superimposable mirror images. Therefore, these two are pair of enantiomers. Therefore, these two hydrogens are enantiotopic, right. So, I would like you to find out the topicity of different hydrogens. I am giving you two examples here for your homework. Find out the topicity of those two hydrogen atoms, considering the chirality of this, which is not identified. So, it can be both R or S. And then in the next homework, you should try to find out the topicity of these faces. As you see here, it is a ketone, and this ketone has two faces. One is from the top of this projection and the other one is from the bottom of this projection. So, find out the topicity of these two faces. The next example or next homework is this molecule. This has two C double bond O groups, namely 1 and 2. Find out the topicity of those faces here, whether they are enantiotopic or diastereotopic. So, what is the way to find out? You try to do a nucleophilic addition reaction as we have discussed in the previous class, and try to find out what would be the product, and from that you should be able to identify what are the topicities of those two faces. So, we will continue from here in the next class. Thank you.